Well, we will start today again in Abaqus presenting a slightly more complex problem using rigid body capabilities or analysis of Abaqus. The problem I would like to present and to discuss with you is seen here on this video. On this video, we have a spring, and this spring is guided via a rod that can freely move around this pin here. Okay, and connected to the end of the spring, there is a little mass. It's a nut here. So this nut then is going up and down, and as it is guided by the rod also does a pendular movement. And so then what happens is this. As you can see, the nut goes up and down, and at the same time there is this rotary movement. So we wanted to model this in Abaqus, and for that I'm going to use a rigid mass as the nut, representing the nut, a spring connecting this point to the mass, allowing this motion and this motion, and the rod is not going to be considered in the model in Abaqus, but could be so um, if we could add the inertia of the rod connected or concentrated on the mass, or to have really a rod as a piece in our model, as a part in our model. So what we'll have here then is we could represent this by a little place for having the motion, then the spring, and then here we have the mass. Okay, so then this is the mass, this is K, the stiffness, and we have here a system X and Y. So then we allow it motion in this direction here and on this direction here. That could be theta, and that could be some kind of x, a local variable. As I said, this rod here is not going to be considered to have any inertia or any properties, so we have only the spring. And then let's see how we build this model in Abaqus. Actually, I did already, and we can see that as we did in previous films of videos in Abaqus, we have a mass. This mass has this rigid point here, okay, and connected to this, which I set to 0, 0, this mass as a reference, a little bit different from what I draw previously. It has inertia, okay, of 0.1. This is not anymore connected with the nut we saw in the video, because I didn't try to match one with the other. I'm just giving some aleatory values. So this mass then is 100 grams. And then I can close the menu of parts, and then I can jump property and go straight to assembly. Okay, on the assembly menu, we can see it on the side here. I created a rigid point, and this rigid point I'm going to connect it with the mass here. Okay, and then the spring is going to be shown now here, has a constant, a stiffness of 100, and a dash spot coefficient, which is the ratio between force and velocity, I set as 0.9. Could be any number actually. So then this assembly menu is ready. We can go now after assembly to step, open the menu here, and you can see that I created this initial step is created by Abaqus, and I created a step dynamic explicit running for 5 seconds. We can change this to 3 seconds, and that would be okay for us to see what will happen. The incrementation also, because I'm not using any finite element in this model, I have to fix the incrementation, because if I put automatic, it's going to give an error, because there will be any length of finite element for Abaqus to evaluate the time steps. So I put fixed with 10 milliseconds as a time increment. Okay. So this is done with step, or I still kept 5 seconds, 3 seconds here. This I can dismiss now. After the step, there is no interaction. I can go in load. Load, I can see the boundary conditions here. So there is the boundary condition which fixes this point, and it propagates from initial step to step one. And that's it for the boundary condition. So this is going to be fixed, and this point can be moved along the angle or in the direction connecting the point itself to RP1. As for load, there is no load here, because we are going just to apply an initial velocity for this to start moving. And then this initial velocity we can apply here. First, let's see this boundary condition here. We saw already in predefined field. We can see that we apply a velocity on the x direction of 1 meter per second. Is translational only. We could change here for angular velocity as well, but we apply this velocity for the motion to start. What else we have to see here? Oh, it would be good to have some, no, not analytical fields, predefined field. On this predefined field here, we have the velocity, and here this is computed. Let's see here, where is the here. Here we have gravity. Okay, in load, we can create a load uniform with a gravity of 9.8 in the y direction, opposite to the current y direction here. Okay, and the amplitude is instantaneous, so gravity is present in our model. Of course, the period of our pendulum is going to depend on the gravity value. So this is created in load. Okay, so then I think we are all set for the job. The job I did already before starting the video. Okay, and so then I submitted the job. It finished with no error, and then I can jump the results, and then the results are here. The spring. I could change the position here. I could also go in view ODB display options, and then on entity display I could show the mass inertia elements, apply. Okay, so the mass is going to be here. I can increase a little bit the size, apply. Okay, I can put X here. Yeah, and then I can carry on with the motion. Okay, then we see that it vibrates in this direction and also moves as a pendulum. Okay, that's what we were expecting, and is somehow, if we adjust the parameters, similar to the video we saw in the beginning. Um, I can create, I'm going to delete here just to show you how we do. We can create an XY data from the field output. We can get partial displays, say U2, direction of Y. Here we can go node sets, get the mass, and then we can plot. Let's see what we see. We see here exactly what we would be expecting. Some dominated motion, okay, for the displacement, but in between we have these little motions that one adds to the other to get the overall picture. Okay, dumping is not seen very well here, but we see that this little thing here is keeping changing as time passed by. It went up to 3 milliseconds, 3.1 actually in the 3 seconds on the simulation. But with this, we finished this video where we showed a little bit more a more complex case than just the vibration of a mass in in the actual direction. So here we have the pendulum motion as well. So thank you for watching the video.